G'day chemistry students. In this video, we're going to be looking at dot points 3.3.1, 2, and 3. In this one, we're going to be looking at concentration and its effect on reaction rate. Let's get into it. Now, before we start talking about the chemistry, I want to be talking about the idea of successful collisions and the number of collisions and its relationship. Now, when we're talking about number of particles and number of collisions and all that sort of stuff, a good way of visualizing the concept is the number of people that might be in, say, a wall of death or in a mosh pit. Now, in this wall of death that we see on the right, we see plenty of collisions between lots of people. That's very different to the wall of death that we see on the left, in which there's only one collision with a single person and a wall. Now, the number of collisions in both of these processes were determined by the number of people participating. So we can take this analogy and take it to our particles. If there are few particles, then there are going to be few collisions. If there are lots of particles in a small space, then there's going to be lots of collisions. Now, same process or same idea can be applied to particle diagrams, which we'll see all over the place in the chemistry sphere. And the main idea is more collisions mean that there are going to be more reactions. So in a container like this with particle A and B, because there aren't many particles in the space, the reaction rate is going to be slower compared to the reaction rate of the set of particles below, in which there are more particles put into a smaller space. Now, what that's going to mean is that there are more collisions and thus a faster reaction rate. Similar concepts are being shown in the diagram to the right. In this one, it's showing that the same principles can be applied under aqueous conditions. So we have water molecules in both of these diagrams above and below. They are the aqua color. The reagents that would be dissolved into the water are blue and red. And so similar concept to the one that was on the left. In the one that's on the top, even though the water isn't participating in the reaction, what we care about is the concentration of the particles in both diagrams. Now, higher concentration here on the right is going to mean that the reaction rate of these particles is going to be greater than the reaction rate of the ones on the left because they are in a higher concentration. Similar concepts can be used for solid reagents. The concentration of the substance in the water, the thing that's already aqueous, will still have an effect on the reaction rate in this example because on the right, there are more particles which are capable of reacting with the solid, having more collisions in the same amount of time. And if there are more collisions, it's more likely that there will be a high number of successful collisions, thus increasing the reaction rate. Thank you very much, everyone. In the next video, we're going to be looking at surface area and its effect on reaction rate. But until then, have a good one.